Good evening, everyone. How's that? Better? I want to welcome everyone. I'm Bud Riss. I'm the president and CEO here at the New England Aquarium. We're very delighted to have you here in the Simons IMAX Theatre for the third annual John Carlson Lecture. I trust many of you are here because you share an interest in the world's climate system, perhaps also, like us here at the aquarium, about the role of the oceans in that system. Understanding changes on a global scale, as you all know, is an enormously complex task. I was thinking of the fifth IPCC report that came out just a week or two ago, and it's continued to get clearer over the 5 renditions of that report, stating for the first time that, quote, the warming of the climate system is unequivocal, atmosphere and ocean have warmed, amounts of snow and ice have diminished, sea level has risen, unquote. That much is known and sounds elegantly simple, but documenting exactly what has happened in the past and what may happen in the future, and most importantly, why, is much more difficult. It's equally challenging to try to explain what we know and what we don't know to the public and decision makers. That's why the John Carlson Lecture Series is so important and why we're delighted now to collaborate each year. Indeed, we here at the aquarium share a desire to raise the level of public understanding about climate science and global change. The aquarium, for example, leads a nationwide collaboration now of 30 aquariums and zoos funded by the National Science Foundation and NOAA, working together to figure out how best to educate our visitors about this very important problem. And together we reach almost 30 or 40 million people a year, so it's a great opportunity. That effort, of course, must have a strong scientific foundation under it, which is why we are so grateful to the work done by the Lorenz Center and, again, the intention of the John Carlson Lecture Series to bring that work to the broader public. So I hope tonight's presentation will lead all of you to new discussions about global change with your colleagues, your family, and friends. By having such discussions, you too can help to share good information and raise awareness. I'm happy to be joined tonight by Kerry Emanuel, Cecil and Ida Green Professor of Atmospheric Science, and Daniel Rothman, Professor of Geophysics, the co-founders of the Lorenz Center and MIT. And I'm going to turn the mic over to Dan.
Thank you, Bud. Welcome to the third annual John Carlson Lecture. This lecture is made possible by a generous gift from John Carlson, John Carlson's gift to MIT's Lorenz Center. I'd like to spend just a couple of moments remarking about 2 wonderful benefits of John Carlson's gift. First, which is quite obvious, I'm sure, to everyone in this room, it provides a way of communicating basic climate science to the general public. In doing so, the Carlson Lecture also honors the legacy of Ed Lorenz. Professor Lorenz is widely known as the father of chaos theory, which he discovered as part of his studies of the predictability of the weather. Such curiosity-driven research, performed in the context of an important practical problem, epitomizes the spirit of the Lorenz Center. Tonight's Carlson lecturer, John Wettlaufer, is professor of applicable mathematics at Oxford and professor of geophysics, physics, and applied mathematics at Yale. Now that's a mouthful, but the reality is actually quite simple. John studies the physics of ice. Right? His work has helped explain problems ranging from why ice is slippery to how glaciers flow. In particular, the implications of his work for improving our understanding of climate has attracted much of his attention and that of his colleagues. One of the remarkable aspects of John's work is the way he combines fieldwork in the Arctic, laboratory experiments in his own lab, and mathematical theory. This interplay between theory and observation, so central to basic climate science, is, as you shall soon see, also one of the main and most intriguing features of his work. So without further ado, let us welcome John Wettlaufer.
Can everyone hear me? No? Yes? No?
Yes. Yes. Well, thank you very much. I want to thank Carrie and Dan and John Carlson, the Aquarium and MIT for inviting me to help celebrate the aspects of the legacy of Ed Lorenz by taking you on a kind of tour of my particular view of what we understand and what we don't understand, and why, and how it sort of fits into the pantheon of physical sciences. Now, I don't often get a chance to stand in front of this big screen like this. When we were in Stockholm last year, we used to go to the Natural History Museum and go to the IMAX Theatre all the time. And when my son finds out that I was standing here and didn't come out of the screen, he's going to be sorely disappointed. Okay. And I'm going to have trouble sort of seeing where I'm going, but this is a picture of the way in which people who do geochemistry try to understand the fluctuations in our past climate. I'm not going to dwell so much on this, but to say that there are proxies that allow one to look at the temperatures in the past climate, and this is one of them showing you over, well, the kinds of timescales that you're not used to sort of digesting, how the temperature has changed. And you can see on the right-hand side there is the temperature and the past. And as you go from that side to this side, you go from then to now. And, sorry?
Just looking for the other mic somewhere.
Is there feedback?
I think there's, do you have the other mic? It's off. It's off. Okay.
Okay, so you see these wiggles, and you see dramatic changes in the past climate record. You see that ice in the southern hemisphere is a rather new entity on the time scale of 60 million years. And in the northern hemisphere, it's even more of a recent phenomenon. So it's very clear that there have been serious changes in the past. And the question is, what's going to happen in the future? Okay. All right. So this is a very well-known physicist who is accounted with making this statement. It's certainly true. And the answer is, of course, we're not sure. Okay. So let's just delve into the issue of prediction. What's the nature of scientific prediction? Okay. And in fact, what is the nature of science? Okay. So of course, I don't know all of you people. I don't know how many of you decided that you would abandon the nature of science in the past and never think about it again in the future, or whether you have a good idea of the nature of science and or your particular view of what science is. Okay. But let's just start with that question, and we'll use one of the great teachers in my field, Richard Feynman, who made this profound statement, which is true. Science is a way of trying not to fool yourself. And the first principle is that you must not fool yourself, but you're the easiest person to fool. Okay? It's true. Okay? But it's a deep statement that there are things that just are inviolable, and one of those is that you can't really deceive yourself. And the construct of science is really essentially based on this idea. We could ask, why do we need it? Okay. And I'll turn to something that's rather more common for most people. How many people have a cell phone? Right? How many people are extremely annoyed when you don't have any bars? Right? How many people think it's their right to speak on their phone at any time, in any place? Okay, we'll stop there. Okay. But you demand that the technology works all the time. You drive your car, you use your computer, you're very surprised when it crashes, and in fact, it's very rare that it really does, given the amount of time you use these things. Okay, so we often equate technology with science, which is, they're obviously related. We need science for repeatability. And repeatability is equal to safety. If you are old enough to remember the Challenger disaster, I remember exactly where I was when it happened. The question of what happened there has to do with repeatability and safety and a scientific principle. And I refer again to Feynman, who says a successful technology requires that reality must take precedence over public relations, because nature cannot be fooled. And he was asked to be involved in this investigation, and his questions were focused on scientific issues. What could have gone wrong? And as you may know, that the O-rings for the solid rocket boosters did not have a high enough thermal expansion coefficient, and that was the origin of the problem. And he sort of demonstrated it here when he did this experiment.
Took the stuff that I got out of the receiver and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it maintains, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
Well, I mean, the echo wasn't really part of the original video, but you see what he did, right? I mean, he tested the very simple scientific principle and saw that there was no resilience in the O-ring. Okay. So one might generalize this statement he made to our problem. For the successful understanding of climate reality must take precedence over public relations, for nature cannot be fooled. So it really is true, when we think about Ed Lorenz, that real scientific advances are analogous to those in art. They're driven by human curiosity first, and not by anything having to do with politics. People who are working hard on science are mostly interested in trying to figure out what's going on. What is science not? It's not a producer of absolute and unassailable truth. It's not mere opinion, fundamentally a societal construct with no real objective basis. So it's not that either. It's a tortuous process. There aren't recipes, even though you may have been led to believe that in high school. One makes incremental tests and tries to make progress towards repeatability. Now, anyone who's tried to figure out something knows that exactly what this means. It's a difficult process, and it's best described by Feynman.
When you're thinking about something you don't understand, you have a terrible, uncomfortable feeling called confusion. It's a very difficult and unhappy business. And so most of the time you're rather unhappy, actually, with this confusion. You can't penetrate this thing. Now, the confusion is because we're all some kind of apes that are kind of stupid working against this, trying to figure out to put the two sticks together to reach the banana, and we can't quite make it, the idea. And I get that feeling all the time that I'm an ape trying to put the two sticks together. So I always feel stupid. Once in a while, though, the sticks go together on me, and I reach the banana.
Anyone who knows Feynman would be happy to have some of the sticks that he uses, that he used. So the idea of when you get the two sticks together is really most represented in scientific papers. All of the confusion is usually not published, usually. Okay. What I tell my group is that if they go home less confused than when they came in, they're not doing their job. Okay, so what kind of science do we do? And how do they bear on the particular issues of climate science? Well, there's really two flavors. One is what I'll call laboratory science, in which we probe nature on our terms using controlled experiments. So just to give you an example, here's a picture of the advanced photon source at Argonne. You can see there's this big ring, and those things down at the bottom are cars. Okay, and there's this produces synchrotron radiation, and you can use that to probe the nature of matter on your terms. This is Melissa Spaneth, who I can tell you definitely probes nature on her terms. She built this thing which is inside this box, and then Stephen Pepin installed it right there where his hand is in this sort of simple looking apparatus through which some high energy X-rays are brought in that hole in this little object there. And my point only is to say that one takes data, which this data doesn't really particularly matter, except for if you look at the horizontal axis where it says scattering vector, the units are 1 over angstroms, right? So 1/10,000th of the diameter of your hair. Okay? So one can go and probe nature on their own terms. And that's a style of science which is, you may be familiar with, but it's rather different than the sorts of things one might do in many areas of climate science. So the other flavor is based on observations rather than experiments, if you will. And in that case, one probes nature on its own terms. Okay. And so we have sort of different lab coats. The working day is constrained by various things. I won't ask you whose hat you think is best. The practical considerations differ rather more than those that one encounters in the laboratory environment. Okay. And so you can imagine that people, when they have gone for some period of time under these conditions and have made observations, that they're pretty serious about not, about every data point, right? Because it's sort of hard-won material. But then you have some observations of nature on its terms. And the question is, how do you simplify or unify a complicated system? How is it that one addresses geophysical scale issues in a meaningful manner with local observations? This is a major challenge in this area. Okay, so now let's start to take a view from the north. You may recognize this object. It's an artist rendition of the globe, clearly a North American artist, right? In about June. And so you recognize there's Greenland here, and then this, it's hard to see because this doesn't really show up there. But you see the white cap at the top is the Arctic Ocean. And every year the Arctic Ocean freezes, and a thin vernier, relatively thin vernier, persists perennially. It's about 2.5 meters of ice, and it grows, it decays, it grows, it decays, it grows, it decays. We'll look at that in a moment. Its importance is multi-fold. When it grows, it rejects salt into the ocean and drives circulations that couple to the global ocean. When it expands an area, it increases the albedo of the surface of the planet. The albedo is the reflectivity of radiation. Okay, so white things have a much higher albedo in the visible than do dark things. Okay. And so it's commonly said that the Arctic is a bellwether for Earth's climate system. And let's start to parse out why that's actually discussed. Now I'm going to show you a movie here, sped up over 6 years. And so the color there is this is looked at from satellite. It's the microwave emission of the surface of the Arctic, but the color is the ice. Okay? And you can see it waxing and waning. That's the ocean freezing. And that ice that froze is then ablating every summer. And as far as we are aware, this has been going on for at least several million years. So it's cold in the winter, it grows. It's warm in the summer, and it melts back. Okay. And here is, from the satellite era, from 1979 until now, this is the oscillation. It grows, it decays, it grows, it decays, it grows, it decays. And so I refer to it as an albedo oscillator. As the area of white stuff increases, then the area of reflectivity increases. And as it draws back, the opposite occurs. Okay. So now let's parse out what this really means by a simple argument which appeals to your common experience. Okay. Right, so you're familiar with not touching the burner, okay, especially those of you who have children. Don't touch that. It's red hot. So as you heat up something, it radiates at a different color, okay, or frequency. So it goes from red hot to up to white hot. Okay, and you see that, the visible emission of the material as it's heated. Now there's other parts of the spectrum, the electromagnetic spectrum, that of course you don't see. You don't see the microwaves that are cooking your food. You need a special way to look at the microwaves. Lately, there have been energy audits. Has anyone had an energy audit of their house? Right. How much did it cost you? Okay. It's free. Good. So they may have come along with an infrared camera. And so all day long, it's sun's coming, is out heating up the earth, and your house, when it's leaking heat, they can take a picture with an infrared camera. Okay. So you can't see that without a camera which is tuned to the certain part of the electromagnetic spectrum. And so the Earth is doing that. The Earth is receiving the radiation from the sun in the visible, and it's emitting in the infrared. And you can see here, this sort of cartoon shows that there's a separation, right, in the temperature associated with this part of the electromagnetic spectrum. So the Earth system really at its core is driven by this process. We get visible radiation from the sun. It heats up the planet as a system. The system is re-radiating this energy in the infrared. Okay, so how do these things balance? So if you're not familiar with these things, radiation flows. You know, you hear this, it's flowing. If you put your hand in front of a hot computer, you feel something, thermal radiation. Okay. So it's just like the flow of liquid. So the flow of radiation you can think of in exactly the same way. I don't have much use for a gravy boat like this anymore, so I did this little experiment. And you could see, we talk about what's called a steady state. The flow in equals the flow out. when the system is in steady state. You know that because the level doesn't change. And you could have a different flow in and a different flow out, but if they're the same, then the level will never change, so long as I can stand there and hold this. Okay. So you could think about their system in a similar way, very crudely, that there's incoming radiation from the sun, and a fraction is reflected by the planet. That's the albedo, which we call alpha. Some fraction is reflected, and therefore 1 minus that fraction is absorbed. Okay. So we could balance those two things, treating the planet as a big rock. And when you do that, you get the following instructive result. The fourth power of the temperature of the Earth is proportional to the solar constant times this quantity here, 1 minus the albedo. So if the Earth was completely white, the albedo would be approaching 1 because all the visible radiation would be reflected. And so you could see clearly as the albedo increases, 1 minus the albedo decreases, and so the temperature of the planet decreases. So the more white stuff you have covering the planet, the lower the temperature will be in this radiative balance. Okay. So that's the main message from such a simple argument. And if you just put in numbers for what we roughly estimate as the planetary albedo, then you get a temperature of about minus 15 Celsius or 5 degrees Fahrenheit, which is pretty cold, right? Even for Boston. Right? Okay, but it's pretty close given the really crude estimate. I mean, it's not 1,000 and it's not a millidegree. It's pretty close. Okay, so what's wrong with the artist's rendition? Clouds. Right, so, you know, the atmosphere, for a start. I mean, we could quibble about the artist. So, but, okay, so the atmosphere. So if we go through the same argument and just crudely put a layer of the atmosphere, one layer of the atmosphere, and that atmosphere is going to absorb the outgoing infrared radiation and re-emit some of it back and emit some of it back to space. Right, so you know when it's a cloudy day here, it can be very warm, notwithstanding the humidity. So if you just do that exercise, you find that the temperature of the surface increases by about 1.2 relative to the previous number. And so then one gets a value of about 86 degrees Fahrenheit, which is, of course, pretty warm, too. But you see the qualitative trend. And, of course, what a scientist would do is to start putting in more layers and start putting in more complexity and trying to figure out, what controls the temperature of the surface of the Earth. But my point here really is that the albedo is a very important quantity. And that albedo, if it increases, the planetary temperature decreases. And when we look in the polar regions, we could see this veneer of ice really playing an interesting role in that regard. You have regions that are very reflective with high albedo, and you have the open ocean, which absorbs a great deal of radiation. So the albedo of the ocean is about 0.2, and the albedo of this ice is about 0.65. Okay, so this idea is invoked in what is called the Ice-albedo feedback. So you can imagine, here I've just drawn a cartoon with the ice extent over there and an increased value of radiative forcing. You could imagine turning up the sun, for example. And the blue curve is the case where you have a lot of ice say like we have today, and there's a lot of radiation being reflected. Now you could imagine warming the system and increasing the areal fraction of water relative to ice. That will allow more radiation to be absorbed into the system, which will heat up the water, which will melt the ice. Okay. And eventually, one can theorize that there's a threshold beyond which the ice extent will drop from this value up here on the left to a low value. Okay. We call that a bifurcation point. It's really something that people worry about. Now, practically speaking, whether the curve looks like the one on the left or the one on the right is probably not an issue for humankind, per se, but it's a scientific issue for us to understand what's the nature of the transition. Because the one on the right is reversible. That is, if you reduce the radiative forcing, you just increase the ice extent. Whereas this one requires you to go all the way back to where the dotted red line hits the lower blue line and then jump up. Okay? So you can see those transitions are qualitatively very different. And this is at the heart of the question about what's happening to sea ice in the Arctic. So you read about it all the time because reporters have to say something's happening. But this is why. You can go to this website, which is Cryosphere Today. Bill Chapman has been archiving this data, and you can go and look at any day, look at your birthday, see what the ice cover was. The ice grows, it decays, it grows, it decays, it grows, it decays, as we saw in the video. And what people are discussing is, will there be a point beyond which there will be no ice in the summer and only ice in the winter? We would call that seasonal, a transition from perennial ice to seasonal ice. That is, there would be no ice at about late August and early September. Okay? And that's this transition that people are focused on. And now you see here, the dates are in the lower part. This is the 1st September of the satellite era. And this minimum here in September of 2007 made people say, well, there's some transition. Because it was the largest minimum, if you will, the smallest amount of ice in any September that had been recorded relative to the previous year, which was 2005, by about the area of Alaska plus California. So there's a major change in the area extent of the ice. So now I'll flip to moving September 2007 to the left, and we'll just go up through the September since then. So you see what happened in 2008, and then 2009, 2010, 11, 12. That one got a lot of press. And then just last year. Okay. So you might say, well, what does this have to do with the price of tea? I don't know. How should we approach the problem? There are basically 3 scientific approaches one can take. You can make observations, as I've sort of discussed. There are 2 real types that are geophysically relevant. One is what I would call a low-resolution paleoclimate data. That is, it's low. The very first figure I showed with all the wiggly lines is very coarsely resolved in time. Okay. And the data I've just been showing you is daily. The satellite data, that's daily. So that's about as high of resolution as one can get. One can run a model. I'm going to delve into this slightly in a moment. Global climate models. Have you heard of them? People hear of them? Yeah, big complicated models. And the kind of things that I do, which are based in the approach of theoretical physics, that are constrained by observations. Okay. So I claim that to understand the system, no one of these approaches is sufficient, and that all have different types of uncertainties. Okay. So this is nearly the state of the art of global climate models in predicting what happens for the next 100 years or so. So all of these on the right-hand side are the state-of-the-art climate models. And that red curve there, the thick one, that's what the ice is doing. Okay. I think it says something on its own. I don't need quite to say much. What this is an example of prediction using these models. Now, in some sense, you can interpret the left-hand side as an error, and so you may realize that there's a substantial error or variability amongst the models. Okay. Since I'm focusing on Feynman, I'm going to start talking about our ability to think about uncertainty. And he espoused this idea that really it's the essence of what we know, is knowing and understanding the uncertainty. So why do we struggle with uncertainty? It's an interesting question, right? Yeah. I mean, certainly we all know in our common experience that there are types of uncertainty that are acceptable, but others are not. So, for example, right, you're okay. Oh, yeah, the stock market dropped. It's up. It's down. It's up. But I want a retirement, right? I don't know. Other examples. You plan your vacation. Do you plan your vacation based on the weather forecast in 3 months? Right. Okay. Do you plan your vacation based on the climate model prediction in 100 years? Well, okay. So clearly, I mean, living with uncertainty is very easy so long as it's your uncertainty, not mine. Right. So let's start to peel back those things here. Here's a picture of the atmosphere at about 10 kilometers, the moisture in the atmosphere. And this is a really beautiful movie. You could watch this for a long time. The atmosphere is viewed as a fluid sitting on a rotating sphere, and we understand a great deal of the basic dynamics of the atmosphere. And trying to predict it in the sense of a weather forecast goes back now to Louis Fry Richardson, who was a polymath, and he was the person who first conceived of numerical weather prediction. That is, solving the differential equations which describe the fluid in the atmosphere on a computer. But on a computer in 1922, no computer. So he conceived of this great hall of people. You could see all the people, each sitting there with a pad computing the solution to their equation in their grid box and handing it to the person to their left. But really, the conceptual idea was started there. Little did he know, sort of before that, was another polymath, Henri Poincaré, who, amongst many other things, had an insight that if you didn't really know the initiation of your model extremely well, just small differences would lead to very different solutions. And it was Ed Lorenz who was really extremely curious about this and tried to make a very simple model, one might say crude model of convection in the atmosphere. And as we heard earlier, he invented the idea, which is now called chaos. And you can see these two curves here. Just an example. You see there's a blue and a red curve. And at the beginning of their evolution, the horizontal axis is time. They're sitting on each other. And then after about a time of 7, they start to go wildly different. Okay. And the difference between these at the initial time is minuscule. Okay, so small differences were amplified. And this is really at the heart of the problem of you being able to plan your vacation within, beyond about 10 days. Okay. And of course, we could ask, well, see, if the climate is just the weather on a long time scale, what does that mean? Okay. These are questions people ask. But here's the climate, right? Here's the Earth. Look at all this stuff happening, right? I mean, you have all of these different processes that one must try to model. Everything from biology, to evapotranspiration, to the ice cover, to the sea ice, to the ocean. Is what people are trying to put into a climate model. And if you put it on a sheet of paper, it looks, just like this. I mean, this could be a management plan. Could be your tax return. That's John's tax return. Okay, so just to give you a qualitative idea, you see all these boxes, and there are arrows coming into them and going out of them and coming into them and going out of them. And you could study the corpus of these, which is in climate models. Or you could ask questions about subsets of them that you think are good motifs for a big process in the system. Okay, so let's imagine that we have 5 components of the climate system, okay, as metronomes. Okay. Now we need, they're all sitting there, uncoupled. And now, so when they began, they were all doing their thing independently, components of the system that weren't interacting with each other. And now they strongly interact and they go in sync. Okay. So it really matters how the arrows go in and out of the subcomponents. Right? And then you could uncouple them. Right? Now, this is a simple system. Okay. Okay, so one last topic, the different type of uncertainty. And there's a field which is called statistical mechanics, in which one tries to understand how the microscopic constituents of a system create the macroscopic response. So we know the room is filled with air molecules. How is that fact useful in us determining what the temperature is here, or the pressure? Okay. And in so doing, we can't see all the air molecules. And so we abandon the certainty of knowing where each molecule is in return for having it guaranteed in some other way. Okay. So a classical example is what is called Brownian motion. And here's a nice macroscopic view of it. There's a ball you can see sitting there, and it's sitting on small particles which are being shaken. And you see the small particles are colliding with a big particle, and it moves it around in a sort of way in which you see a mosquito coming at you. So all those collisions, you can't keep track of all the small particles. But you can watch the big particle move around. And Brown, after whom this is named, watched pollen grains in water under the microscope. And he could see the pollen grains move around just like these black particles here. They were being impinged upon by the motion of the water molecules, but he couldn't see the water molecules. But you know they're there. Okay. And you can calculate the sort of displacement of one of these particles due to the invisible water molecules that are colliding with it. And the position is proportional to the square root of time. Okay. So that is, you watch your watch and you count off how much time is transpired, and the particle will be, on average, displaced according to this formula. But that number there, d, isn't just any number. The value of that depends on all the correlated collisions of the invisible fluid molecules. Okay. And this measurement that was made was really one of the first pieces of evidence for the existence of molecules. In fact, the Avogadro number, which you may have heard of, comes right out of this analysis. So these collisions of water molecules have a real effect. You can't ignore them, but you have to abandon the idea that you're going to trace the trajectory of each of them. Okay, so let's return to this. We've been watching these things shake and jiggle. And now we might see this time series in a slightly different way. You see, as the ice advances and retreats, it doesn't do so exactly the same way every year. The edges of it are different. The oscillation is overall the same, but the details vary. So one might imagine that it's being shaken, or there are collisions, there are events that are very fast that are influencing it, but we can't actually say exactly what they all are. Okay. Well, if you have an afternoon or 365 afternoons and coffee, you can sit around and, in the spirit of Brownian motion, you could make a model that deals with such things. And if you do that and you ignore these collisions, these fluctuations, and just make a prediction of what happens to the ice in exactly the same way as we looked at earlier, you increase the radiative heating, you get a curve like this. The blue curve says is where we are now with all the ice all year round. And then there's a transition for when you only have ice in the winter and no ice in the summer. And that seems relatively peaceful. And then eventually you get up to this point here, and you jump up to where there's no ice, because the ocean has heated up so much that you can't get the heat out next winter, and no ice forms. And then to get back to where we are now, you have to cool down farther than you were when you started, and it jumps back down like that. And that's what happens if there's no shaking or fluctuations like in Brownian motion. So you can ask yourself how you think about that. One way to think about it is if you put a marble, for example, in a sombrero, the sombrero is what's controlling the long-term behavior of the system in the absence of noise, and then you start shaking the sombrero, right? You move it to the left and the ball goes up, and you move it, the ball goes down, and then it goes to this other state, and you keep doing that. And it really matters then how quickly you're shaking the sombrero. That will tell you how long a ball stays in one part of the system versus the other part of the system. So this is a motif for what might happen. It's a sort of mathematical idea translating some aspects of one field into another field. But now you could start searching for what would be the source of the shaking. Okay. And there are many potential sources. The one that we focus on ourselves is the albedo of the ice, the reflectivity of the ice. I mean, here's a scene in March, the same scene, this ship here in September. Okay, that's coming out of winter, and this is at the end of the melt season. And you can see the distribution of the water on the surface. Right? It's not going to be the same every year. Every year it'll be slightly different. The distribution of the dark stuff on the ice will be slightly different. Okay? And you could view that in a kind of what we call a stochastic way. Okay? And you make some qualitative predictions, and here are some of them. As you increase the radiative forcing in the system, you see the top figure is sort of about like you might expect now. Of course, this is just a way to look at qualitative changes, but where 0 is, where the horizontal line is the boundary between when you have ice and when you have ocean. And what you see is that for a long time, the system can have no ice on the ocean, and then it comes back. And it goes away, and it comes back. I wouldn't put any particular value on these numbers here. I just figured it was the time I had till I was going to retire. But as you increase the heating, look at this qualitative change. You have the dwell time, if you will, of the state without ice is very long. So whole careers will go by. Okay, so that in the end is really the message of one approach to trying to understand aspects of the climate system. And that is that these simple models, which I really haven't showed you the underbelly of, I've just showed you some of the consequences of, have a benefit of being, well, sufficiently simple that you can analyze them thoroughly. But the challenge, and the perennial challenge, is to understand how much complexity is necessary to achieve what one might call realism. Okay. What's that balance? Okay. A well-known person said, make everything simple as possible, but not simpler. Okay. In some sense, I don't know what that means. Right? What does it mean? How much simplicity is it driven by fatigue, the lack of creativity, or how it compares to observations, and which observations does one use to compare? And as I like to say to my group, even the most perfect situation is nothing more than an exquisite compromise. Okay. So with that, I do want to recognize some of the people I've worked with. There are two students, Sahil Agarwal and Woosak Moon. Ian Eisenman, who started off as a student working with me on this work and is now a faculty member at UCSD. And Norbert Untersteiner, who's passed away, was the person responsible for me in the first place getting involved in this interesting area. And I thank you very much for your attention.
Good evening. I'm Kerry Emanuel. Is this live? Can you hear me?
No.
I did turn it on. Okay. I'll take questions for the audience for John. If you're going to ask a question, please stand up, speak up clearly so we can hear you, and I will probably repeat the question before I turn it over to John to answer. So questions? Yes?
Okay. I guess I understand about uncertainty. I'm a scientist. I know about that. So the question is, when you need to act and when you need to convince other people to act, how do you present the uncertainties, and how do you deal with them and ask other people to deal with them?
So just to repeat the question, if you as a scientist understand the uncertainty, what's the strategy for communicating it?
Oh, boy. Strategy, I don't have a strategy. If I had a strategy, so in this area, there are people who are working scientists who spend a great deal of their time focused on just this issue. And I'm not one of them. Okay? So that's a cop-out, but it's a fact. There's just, so I don't have a strategy because I don't work with the kind of models that make a prediction for what the temperature is going to be in Pittsburgh in 100 years' time. So that's not what I do. I do these things that you can write on a piece of paper, trying to predict sort of the qualitative effects. I would call it qualitative physics that I can interpret. Okay, but the back of the envelope calculation, that to me is something that is a reasonable thing, because if I'm talking to a politician, what's the politician going to understand? I don't even know what the politicians understand. We all know that. So, I'm sorry that's a bit of a cop-out, but that's not what I do. There's a whole industry of people who talk to the press and say this is going to happen. And I think that it's pretty clear that if you do certain things to the extreme, certain things are going to happen. Exactly how it goes, it's like one of these things. I show you a plot that has a time scale of 60 million years. Okay, you look at that and you look and you say, gee, when it was warm, right? And, oh my gosh! And you look at the back, but in the record, and you see, well, there's a correlation between how warm it was, which is a measurement, and other things. And you say that's reality, and that can happen. Okay, and then you come to now and ask, how is it going to go forward in the future? It's very weird then. So now I'm way off my area of expertise. It's all about psychology, because I talked about uncertainty in psychological situations. I know what it's like now, and what's going to happen next year. That's all about the human time scale, right? So if I put water on a burner and I put it on high, damn well it's going to get hot. And about in 5 minutes, you better go back in the kitchen and pull it off. Okay? When you talk about this stuff, that's therein lies the sort of gap. But I think the evidence that people usually talk about that they think is compelling is to look in the past record and say, there's nothing to expect that there will be a different feedback that would change this. And people argue until they're blue in the face about those things. But I myself, in terms of a strategy, I don't have a strategy. I just want to get through the day.
Yes.
Maybe you've already answered the question, but I'll ask it anyway. Can you and have you predicted how long it will be until the ocean rises, let's say, 10 feet?
So the question is, have you, or can you and have you predicted when the ocean will rise by 10 feet?
You know about my investment in waterfront property in Pittsburgh? No, sorry. No, I haven't answered it. No, I have no idea.
Yes, there.
One thing strikes me in looking at your time-lapse photos, and that is the area you're studying, the Arctic, looks like a relatively small percentage of the surface area of the Earth. Is what's going on in the Arctic enough to drive climate and temperature for the whole ball of wax?
So the question is, The Arctic, although very interesting things are happening in the Arctic, it's only a small fraction of the planet. Is it enough really to affect what's going on globally?
Yeah. So Wall Street is a small fraction of the... sorry, just kidding. I couldn't resist. But still true. Right. So slightly more complicated approaches, but not entirely, than what I work on, demonstrate, at least within the constructs of the model, that really it is it's got a much larger impact than would be reckoned by its area alone. And the reason is, that the cold polar regions are the sort of sink of heat that goes from the low latitudes to the high latitudes, and a lot of it escapes to space. But if you look at the total energy budget above the polar region, and you measure the heat going out to space, you can trace 1/6 of that heat just to the latent heat of fusion of the ice. Okay. So, just the ice growth is a non-trivial fraction of the energy budget in the polar regions. Now, the question about how it couples to the rest of the climate, you have important feedbacks. The one I mentioned in the first place has to do with the transport through the atmosphere. The one that I am also interested in, it has to do with what happens in the ocean. The Arctic is a basin which is connected to the global ocean by what's the Frem Strait and the Bering Strait. And you may have heard of deep water formation. This has to do with the cold water that's very salty, formed in the polar regions, which sinks and makes its way southward. And so if you change the extent of the ice by a small amount, it changes a balance which controls the convection in the polar regions, in both polar regions. And so while it looks like a small fraction, there are physical processes that make it more strongly coupled to the rest of the atmosphere-ocean system.
Any questions on this side of the room? Yes.
I was wondering what your views were on the studies done by the University of Hawaii. On the recently published studies done by the University of Hawaii, they're talking about the climate change in the tropics.
I think you may be referring to a recent paper in Nature about extremes and how they compare today. Do you know which paper he's referring to?
Just stand here.
Okay, now you can go.
I didn't read it. I have no idea. But Carrie did.
No, I didn't read it. I haven't read it yet either.
I'm
yes.
sorry. I'm unaware of it.
It was very recent. Recently, I think, just came out in the last few days, right?
Okay.
Yeah. Yes. There.
The connection between reflectivity and temperature occurs to me. I'm sure it's been obvious, but that the fact that which is most reflective is temperature sensitive is sort of an elegant or horrible coincidence. I'm curious as to what's the second most reflective element of our environment that might not be affected by temperature.
So the question is, if ice is the sort of most reflective substance in the climate system, what's the second most important, and is it as sensitive to temperature as ice is?
Okay, it's a great question. Second most, so one of the things that is essential in the planetary albedo is the extent of clouds. And there's a really big problem about clouds, not just because they get in the way of the sun, but they're very difficult to predict in these kinds of climate models because the processes that give rise to the formation of clouds occur on the scale of droplets that are very small. You can't even see them. That's called nucleation. And if I go back to the synchrotron, in fact, and take a thimble full of water and supercool it and try to scatter bright X-rays through it and understand the process by which ice forms in there, I have a very difficult time comparing the experiments with the theory. So that sets the stage for me saying we don't really understand the nucleation of water fundamentally. But now I have a cloud, right, which has got all sorts of stuff and it's moving up and down. And so we understand things like convection and moist convection, where you get condensation and the release of heat and so forth. We understand those, but we can't model them very well. And why do I care? Well, the picture I showed, with clouds, what are the clouds? They're white. Okay. So they have a direct influence on the albedo because they reflect visible radiation. Okay. And then there are all sorts of indirect and complicated feedbacks. I mean, one of them that people are interested in now have to do with what are called the indirect effects of aerosols. Because aerosols are things, soot that's lofted into the air. They not only does that nucleate cloud water droplets, which can become ice, okay, so that makes more cloud, but they also have a direct effect on blocking incoming sunlight. Okay, and how do they fall into the mix of creating clouds? This is an enormously complicated problem and an important one. So I would say that one, if you were to explain that, then you would go a long way toward understanding planetary albedo. But I'll just maybe Carrie knows.
If I know, I'm not saying.
Okay.
We'll take 2 more questions. I see a lot of, I think, students in the audience. We heard from a few already, but if there are students who'd like to ask questions, we certainly encourage you. Yes.
Hello. Yeah, I was just wondering if you're talking, to someone you met on the street, say, how do you explain to them why what you're doing is important?
Did everybody hear that? Okay. When you meet somebody in the street, he asks John, how do you explain why what you're doing is important? If I got that right.
Now, wait, do they ask me or do I ask? Okay, I'll answer by way of an example. I was at a meeting of a group of material scientists. Now, that's a sort of area between engineering and physics where people try to understand materials. And I gave a talk about what are called lower dimensional phase transitions, what happens in 2 dimensions or 1 dimension. Okay, right, imagine a 1-dimensional solid or 2-dimensional solid. So I gave this talk, and a distinguished experimentalist said to me, well, that was no better than poetry. And I said, well, thank you very much. If I could contribute to poetry, which I can't, then I think that's a benefit. I think the principal luxury I have is the potential to add to the edifice of the way we think about the world. And I think that's important and it has value in the same way that even if you hate Jackson Pollock, his art has value in that way. Do I say it's important because I make widgets or because I have something important I can say about the climate? No. I think it's interesting in its own right. And that has value.
Okay. Yes, last question.
So I found interesting your description of low resolution and high resolution data, sort of low resolution over a long period of time and high resolution. And it seems like the things that you're interested in develop theories to draw them together. I'm not sure what to take away from this presentation, but can you say that we're making good progress in drawing those together. I think a lot of what people would be interested in is a coherent theory, even if it's based on chaos or something, that shows the relationship between long-term data, however coarse, and sort of local high-resolution data that is over shorter periods of time, and develops a rational trajectory for that. I think that's very valuable and interesting at the same time. Can you say something about that?
Yes. Yeah, the question is, you have coarse long-term data and you have some short-term data, and how do you make any use of the combination of these things? That's a rough paraphrasing of what you commented on. So I showed just one figure of what is sort of a geochemical data set over many millions of years. So I work on this problem in two ways. There is an interesting, so the mathematical approach that we use is a particular type of differential equation, which is called a non-autonomous differential equation. It's just a word, but it's got a bunch of interesting characteristics. And you can model things with multiple timescales, right? And so you saw this picture of the well, right? You could have a ball sitting in one part of the well and sombrero being shaken at very, very high frequency. Okay? But then it matters how high the ball has jumped when a particular change in the frequency occurs. Okay? Then it gets over to the other side. And so one can use realistic models to study the general properties of what can happen when you have what are called multiple timescales interacting. Like you see the metronomes, right? I mean, there are very complicated things happening in these simple systems. On the other side, to feed into these models, what we do is look at the time series. So we have 30 years of time of data, 34 years now of data. And we're asking questions. Can you say anything, given that it's this short window, about a time scale that's longer than the window? Okay. So that's a question you can ask. Okay. And you do that by treating the system in a particular mathematical framework that you can then connect to the longer term data. And you can say, are there time scales that appear here that appear in this data? And or what sort of data would you need to see whether there is a commensurability? And this is just, I'm using one approach, and there are a lot of people who are very interested in this. I just talked to Carl Wunsch earlier, who said he was at a meeting with a bunch of statisticians who are now interested in trying to understand these kinds of issues. So I think it's a really important question, because the data stops here. And so the question is, when I'm looking at a little window, is this really just what's happening in the last 30 years? Is it part of a longer term process? And what's dangerous is to extrapolate. Right? You take. Yeah.
Quick follow-up. That's a good answer. Quick follow-up is, so is the current state of the work that you're doing in that area substantiate? Is it unknown at the moment, the result? Or do you feel like you believe it substantiates a net increase in temperature, let's say, of the planet? Is it substantiating the general concern that people have on the results of this work? Or would you say it's unknown?
I can tell you one thing for certainty. If I look at the 32 years of satellite data on daily timescales, okay, I can answer what the cause and effect issues are on timescales that are 32 years. Okay, so. And that's about a serious piece of work. I can say you can see the decay in the ice, which of course you can also see without any fancy method. I can't tell you why. Yeah.
Okay, I'd like to end this evening by once again thanking Bud Rees and the staff of this marvelous aquarium, John Carlson for his generous support, and our speaker, John Wettlaufer. Thank you for coming.